Hey everybody, Mr. C here, and I'm going to show you how to solve Part B of Example 2 of the Section 1.7 note packet, where we're working with a compound inequality, but this time it involves an OR compound inequality, as evident by the way the problem is presented to us. We have 2x plus 6 is greater than 4, or we have 5x minus 1 is less than or equal to negative 11. The strategy for solving this type of compound inequality is to actually solve each of these inequalities separately, one at a time. To emphasize the fact that we'll be solving these separately, I've dropped a little boundary line underneath the word OR, and on the left-hand side of it, I'll have my solution for the first linear inequality, and on the right-hand side, I'll have the solution for the second linear inequality. So without further ado, let's go ahead and solve the inequality that's to the left of the word OR. So just a couple of quick steps here. The first thing we'll do is maybe subtract 6 from both sides. And that's going to leave us with 2x is greater than negative 2. And you probably know what to do next. We're going to go ahead and divide both sides by 2. Now, do we need to worry about reversing the direction of the inequality symbol here? If you answered no, you're correct. That's because we divided both sides by a positive number. So without further ado, we do have x isolated on the left, and we can see that x is greater than negative 1. Let's go ahead and quickly solve the second linear inequality here. We'll first start by adding 1 to both sides. And that gives us 5x is less than or equal to negative 10. Next thing we'll do is divide both sides by 5. And again, no need to worry about reversing the direction of the inequality symbol here because we divided by a positive number. So after a quick few and easy steps, we have x isolated in the second linear inequality. And we can see that there's kind of two different conditions on x here, which is going to play an important role with how we'll form and express our solution. So if you look at our first inequality, this is saying that we can have values of x that are greater than negative 1. Of course, values of x that satisfy this condition on x would be numbers such as 0, positive 1, 10, or even something like 1,000. All right. And our second condition on x is that x is less than or equal to negative 2. What I'd like to do is go ahead and express this answer in a couple of ways. The first way is just involving the inequality symbols, but also the word OR. So what we're really saying here is that, well, if you want any values of x to satisfy this compound inequality, then either your x values need to be greater than negative 1, or the x values need to be less than or equal to negative 2. And an answer such as this is what I refer to as an inequality version of the solution. Another way we can express our answer is, of course, with a graph. So I'd like to go ahead and show you how to do that. And by graph, what I mean is a number line, and we'll shade the parts of the number line that represent our solutions to this compound inequality. Of course, the two numbers that are really important to have on this number line are those that we're comparing x to, and those two numbers would be negative 2 and negative 1. Of course, you want to make sure that you have those numbers in the right order on the number line. And our first shading on this number line is actually going to come from the inequality x is less than or equal to negative 2. And that's pretty much just because negative 2 comes first, going from left to right on this number line. So let's think about it. Values of x are less than or equal to negative 2. Those would be numbers such as like negative 3, negative 4, negative 5, so on and so forth. So the shading that would correspond to this inequality here would be to the left of negative 2, because all numbers to the left of negative 2 are clearly less than or equal to negative 2. So I'm going to go ahead and shade that part of the number line red here. Now when I get up to negative 2, notice that the inequality symbol has a bar underneath it. That means that we're allowing for x to equal negative 2 as part of our solution. So for that reason, I'm going to use a bracket, and I'm going to have it oriented towards the direction of shading. Now the second part of the shading here is going to come from the inequality x is greater than -1. So think about values of x that make this work. Those would be numbers such as like 0, 1, 5, or even 10 trillion, just to go nuts with it. So for that reason, we're going to shade to the right of -1 because all those numbers would fall to the right of it on the number line. So I'm going to go ahead and shade starting at 1. And of course, we understand that this shading would go all the way up to positive infinity. And on the other side, the shading would go all the way down to negative infinity. Now notice there is no bar underneath this inequality symbol, so for that reason, I'm going to use a parenthesis, and of course that's going to be pointing in the direction of the shading. The next thing we want to do is express our answer using interval notation, per the instruction of course. So you'll notice that we have two different parts of the number line to work with here. Now because this is an OR compound inequality, we want to consider both parts of the shading here as like one unified solution. So what I'm going to do is write the interval notation for the shading here, which is from -infinity all the way up to -2. So parentheses on -infinity by default, then comma -2, and then we'll place a bracket on -2. Now we have the shading that's from -1 all the way down to positive infinity. So parenthesis on -1, comma, infinity. And by default, parenthesis on the infinity. Now we do want the reader to understand that, alright, well, our solution for x can either come from this part of the number line, the part from -infinity to -2, or they could even come from -1 to positive infinity. So what we'll do is we'll link both of these interval notations up with what's called a union symbol. And this is how we would express our answer in interval notation. Now I do want to talk a little bit about the logic behind the OR and how it's a little bit different than the logic behind the AND compound inequality. So you'll notice if we pick the number from, say, the first shading of the number line, like -3, -3 doesn't have to satisfy both inequalities at the same time. As long as it satisfies one of the inequalities, it's a legit answer. So let's think about whether or not -3 solves this compound inequality. Well, of course, if we plug -3 into the first inequality, we would have -6 plus 6, which gives us 0. And 0 is not greater than 4. Alright, so -3 does not solve the first inequality, so hopefully it solves the second inequality, in which case, if it does, then -3 is still a good solution. So let's think about that. If we did 5 times -3, we'd get -15 minus 1, which is -16. And of course, -16 is certainly less than or equal to -11. So even though -3 doesn't solve the first inequality, it does solve the second one. And because this is an OR compound inequality, as long as it satisfies one of them, it's a good solution. Let's pick a number from maybe the part of the number line that's from -1 to positive infinity. Maybe 10. So let's think about whether or not 10 would satisfy at least one of these inequalities. Well, if we plug it into the first inequality, we would have 2 times 10, which is 20, and of course added to 6. This would ultimately be 26, which is certainly greater than 4. So it works here. Let's think about whether or not 10 would satisfy the second inequality. Well, on the left-hand side, we'd have 49, but 49 is not less than or equal to -11. But that's okay. We'll still consider 10 as a solution because it satisfies this inequality. So that's one of the major differences behind the logic when it comes down to a compound inequality involving OR. Your answer for x doesn't necessarily have to satisfy both of them at the same time, and quite frequently there isn't going to be an x that satisfies both at the same time, but as long as your value of x satisfies at least one of them, it's a legitimate answer. So I hope you found this helpful, and thank you for watching.